We're happy to have Masashi Sugiyama with us here. Masashi is a professor in the University of Tokyo and heads the RIKEN Center for Advanced Intelligence Projects, which he started. Sugiyama has been a longtime friend of TTIC, and he's been here many times, although I think it's been a while since he was last here. And has worked in many areas of machine learning, especially having to do with the distribution shift and robustness issues in machine learning. And will be talking to us also today about using weak forms of supervision in machine learning. Thanks.
Okay, thank you, Nati, for the nice introduction. And good afternoon, good morning, good afternoon, everybody. So, actually, last week I was in Montreal and the temperature was -7 degrees, and I was not prepared for it. And that's why I had a bit problem with my voice. Hopefully, I have no problem in giving a talk. So I looked at my calendar a long time ago, and my last visit to TTI Chicago was already more than 10 years ago, 2013. Then there was a 10th year anniversary workshop here, and I was one of the invited speakers here. And that was really a great memory, and it's my great pleasure to be back here. And at that moment, I was at Tokyo Tech in 2013. I was an associate professor there. Then late Professor Sadaoki Furui, so the president of TTI Chicago, he was a former faculty at Tokyo Tech. And he was a professor, and I was an associate professor in the same building. And yeah, we had a lot of nice discussion when I was there. And yeah, so I really respect him, and his leadership was really amazing, and it's my great pleasure to be back to TTI Chicago today. So, okay, I have one slide about myself. So, I'm currently director of RIKEN Center for Advanced Intelligence Project. So, I have a few more slides about RIKEN. So, it's a national research center, and we started the project 10 years ago. Then, I'm a professor in computer science at the University of Tokyo, and we have graduate students there. Then I'm also advising some local startups in Tokyo. So nowadays we have a lot of things. Then my background is basically machine learning basic research, interested in theoretical and algorithmic aspects of machine learning. And I try to spend about 10 years on one topic and try to publish a book. Like I did something about machine learning in non-stationary environments, then still ratio estimation, reinforcement learning, then variational base, and more recently machine learning from weak supervision. Since it's more than 10 years before, so I try to give a kind of overview of our research here today. Then potentially, I'm also interested in applications, but this is way beyond what we can pursue by ourselves. So we always try to find collaborators outside in industry or in other national research centers. Then I did services for conferences like program chairs for New Rips, AI Start, and Asian Conference on Machine Learning. So this is something we started 15 years ago. And also I gave a keynote at ICLEAR 2 years ago. So this was held in Rwanda, Africa. So that was really a memorable experience for me. So that was my first Africa. That was really amazing. Okay, so then I'm from RIKEN this time. So what is RIKEN? So it looks like a acronym for Research Institute for KEN, but it's not really true. And in Japanese, so RIKEN is written in this way, 6 characters. They are pronounced as Rikagaku Kenkyusho, and the first 3 characters mean physics and chemistry, and last 3 characters mean research institute. And many years ago, RIKEN was called in English Research Institute for Physics and Chemistry, but now we have more like research labs in biology, medicine, computer science, so they have to change the name. Then 6 characters in Japanese is like too long usually. So usually we pick the first character and 4th character and attach them. So this is in Japanese pronounced as RIKEN. Then at some point, the headquarters of RIKEN decided to use this Japanese acronym as our official name. So then in English, RIKEN is no longer an acronym, but this is our formal name. So that's the most important message today. So then here's a brief history. So RIKEN started in 1917 as actually a private foundation. So part of the funding was donated from the emperor's family, I heard. And after that, RIKEN got bigger and bigger, and it was called RIKEN Concern. And in 1939, RIKEN had 63 companies and 121 plants. They were really successful. But because of this big success, RIKEN was regarded as a kind of dangerous entity. And after the World War II, RIKEN was broken up, unfortunately.
Wait, so I'm curious, what did what did these plants and companies do? Is it mostly like chemical manufacturing or what?
Yeah, so chemistry and physics. So some medicine and a lot of things are developed.
But they're actually like also manufacturing and. Was it just research?
Like vitamin tablet, for example.
Okay,
many things actually. So then after that, in 1948, so RIKEN restarted as a scientific research institute. Then later on, it became a public corporation. And now it's called National Research and Development Institute. So we are under the Ministry of Education in Japan, and we are pure national institute. Then entire RIKEN is quite big, and it has 2,900 researchers and 500 admin staff. And roughly, there are 15 research centers and projects. And there are like 6 physics-related research centers, 6 life science and medicine-related centers, and 3 are computer science, informatics-related centers, like robotics, supercomputer, and our center for advanced engagement project. So this is our center, RIKEN AIP. So what is it? So RIKEN founded the Center for AIP in 2016 under the Ministry of Education, Culture, Sports, Science, and Technology. Then here we have 140 researchers, and we have quite a lot of international researchers and female researchers. Then we have about 300 visiting researchers from different universities and from some companies. Then 120 domestic students as part-time researchers. Then 190 international interns, not only in summer, but through the year we are accepting internship students. Then, so we are located in the center of Tokyo, so we have visitors from TTI often. So whenever they come to Japan, usually they come to Narita Airport or Haneda Airport in Tokyo. So then they anyway need to come to Tokyo Station. So our office is 10 minutes walk from the Tokyo Station, so located in this building on the 15th floor. First 4 floors are the shopping mall and restaurant, so it's quite convenient. Then in this office, we have a big discussion space like this. Often we have visitors and talk and discussion. And in addition to this Tokyo office, so many team leaders are coming from different universities, and they are part-time. They are professors in different universities, and they are part-time team leaders at RIKEN. So then we decided to distribute our office in each university. So from Sendai to Nagoya, Kyoto, Fukuoka, we have distributed offices. Then in RIKEN AIP, so we have 3 research groups. The first group is called Generic Technology Research Group, and here we have 13 teams. So they are doing basic machine learning research, like learning and inference algorithms, statistical and optimization theory. The second group is called Goal-Oriented Technology Research Group, and here, so we have 18 teams. And roughly they are categorized into two pillars. And the first pillar is AI for science, so this is quite important nowadays. And in Japan, we have a lot of national projects on cancers, material science, genomics, and we have a partnership with those institutes, and we are pushing their research through AI. Then the second half is AI for societal problems. So we are a national institute, so we try to tackle public problems like natural disasters in Japan, like earthquakes, tsunami, elderly healthcare, and education. Then finally, AI in Society Research Group. So here we have 6 teams working on personal data management, AI security, economy management, and ethics and governance, things like that. So all 3 groups are quite different and diverse, but we try to have joint project together and explore new topics around. Okay, so that was about RIKEN. And so we started in 2016, and it was originally a 10-year project, and we are almost finishing the first project. But already internally, so our president said it to make our center kind of permanent. So we will have at least keep the same form for the next 7 years. So hopefully, so after the talk, we can discuss a bit more about future possible collaboration between TTIC and RIKEN. Okay, good. So coming to the research part. So today I want to talk about reliability of machine learning, because nowadays reliability can be degraded by many different factors. Like for example, our training data does not contain sufficient information for training the classifier, or maybe labels are quite noisy due to human error or sensor error, or maybe our data is biased due to changing environments or because of some privacy reasons. So we are not allowed to collect data as we want. But then, so our training data is biased compared to this distribution. So we want to overcome these issues. So that's the challenge here. And today I want to give a kind of overview of research in the last 10 years or so, briefly. Okay, then let me start from the first topic, weakly supervised learning. So we know that supervised classification from big level data is quite successful in many applications. So some are already superhuman. But still, there are many applications where big level data is not available. Like in our RIKEN center, so we have projects on the medical research, natural disasters, robot control, brain signal analysis, etc. So in these applications, so collecting level data is quite challenging. And we have a lot of earthquakes in Japan, but still it's far from big data, so we need to cope with it. So then, ideally, I want to say that, okay, we do machine learning from small data, but learning from small data is not always possible statistically. So instead, so we decided to consider so-called weak supervision that can be collected easily. So I don't say, so we only use small data, but we use large data, big data, but still, they don't contain enough information. So that's a challenging problem here. And one of the typical examples is called PU classification, positive unlabeled classification. So here we consider just standard binary classification problem, so separating positives and negatives. But in this PU classification scenario, we only have positive data and unlabeled data without having any single negative data. So the task is, so given blue points and black points, we want to separate blue and red. This is the task of PU classification. We have been working on this topic for more than 10 years now, and we have a kind of nice systematic solution. So let me quickly go through some basic ideas. So the goal is the same as standard supervised classification. We want to learn a classifier f of x that minimizes the classification risk. So here L is a point-wise loss function, like cross entropy loss. Then this is expected over unknown true distribution. And we want to minimize this. And naively, we can decompose this one into the risk for positive data and the risk for negative data. And in the standard supervised learning case, we have P data and N data. So we can estimate these two risks easily. But in the case of PU classification, we don't have negative samples. So the estimation of the second term is a big challenge here. So how do we estimate it? Here's a simple trick. So we know that unlabeled data density, P of x, is a mixture of P of x given y equals plus 1 positive data density and negative data density. Like we have positive data density, blue one, negative data density, red one. The unlabeled data density is a mixture of these two. And the mixing proportion is pi and 1 minus pi. So pi is the positive classifier. And okay, today I assume that pi is known, but in reality, we need to estimate pi also from PU data. And this is actually a quite challenging problem. But already there is a series of research on estimating pi from PU data, and it is actually still quite challenging, but we have some practical methods already. So today I just omit the detail and assume pi is known, but in practice we need to estimate pi from data. So that's something we should take care of. Then, so let's use this relation. So marginal is given by the mixture of positive and negative densities. Then, so we can eliminate this expectation over negative term. Then we have expectation over positive unlabeled data minus expectation over positive data density. Then everything can be estimated from PU data only. So we have an unbiased risk estimator naively like this. So that's a kind of quick solution to a PU classification problem. We just minimize it. That's one thing. But still, like this unbiased risk estimator does not work so well in practice. So what we have done so far was to rewrite the risk for negative data with two terms like this and estimated the two terms separately from unlabeled data, positive data. Now suppose the loss function L is non-negative. Then by definition, so R minus is the expectation over the loss. So this is true, R minus is non-negative. But if we estimate two terms separately from data, then this R hat empirical estimate can be negative. Suppose true R minus is 3 minus 2 equals 1. But now 3 and 2 are both unknown, and we estimate them from the data separately. Maybe 3 can be 2, or 2 can be 4. Then it becomes 2 minus 4, and it becomes minus 2. Even though original R minus is non-negative, so R minus hat can be negative. So this doesn't happen in standard supervised learning case, but in weakly supervised learning, we often face with this kind of problem. Then this is actually a big problem. So I took the stochastic gradient iterations on the horizontal axis. And in the standard PN classification, supervised learning case, the blue dotted line is the training error. It decreases like this and it converges to 0. Then the test error also decreases nicely and it converges like this. Once we use this unbiased risk estimator, then it's yellow dotted, red dotted line. So then the training error decreases quite fast and it goes negative like this. Then it converges somewhere. Then interestingly, the test error goes down and goes up here. So when the empirical risk goes negative here, then it overfits. So we decided to apply a simple correction called non-negative correction. We just took max 0 to this potentially negative term. If it becomes negative, we just round it up to 0. Then, yes.
Sorry. To clarify, do you assume that all the positive examples are labeled or some of the positive?
So this setting is actually called two sample setting. So we have two independent sets. So we have a set of positive data points collected, then a set of unlabeled data collected. They are independent. And there's another situation called one sample setting. So this is something what you are discussing. So we have unlabeled data, and then throw a dice, and we observe a positive data.
Yes, if you only have two labels, that's kind of a silly
No,
question.
yeah.
Okay.
But this is like a more general than one sample setting.
No. Sorry.
Right?
No,
My question was a little silly because if you have only positive, you only have two classes and you label all the positive examples.
No,
you have all
that's
the-
what I'm saying,
But
yeah.
it's not the case. I don't think it's the case with all the positive. Some of the unlabeled points are positive.
Yeah.
That's what I'm saying.
And proportion pi.
Yeah,
So right.
that wasn't the case. Yeah.
Right.
And it has to be the case.
And
Right.
yeah.
Either way, you're back to standard.
Yeah, okay.
Yeah. So
Yeah.
thanks for the clarification. Okay, then applying this simple non-negative correction, the performance gets much better. So this yellow line now, yellow dotted line. So this is kept non-negative. It's a training error because of this max 0. Then the test error is kept lower like this. So basically, I gave two recipes here. The first one is to estimate the classification risk in an unbiased way, only from weakly supervised data that we have. Then the second trick is to correct non-negative estimator if necessary. So these are actually quite generic approaches, and we can actually extend this approach to many different weakly supervised learning problems. But before showing that, let me show one example of PU classification. So it's signal denoising, quite straightforward problem. We have noisy speech and we want to clean it. To train a system like this, we usually need so-called parallel training data. So for the same clean signal, we want to have a clean version and noisy version. Then by comparing them, so we can train a neural network to denoise it. But usually collecting parallel training data is quite difficult. Then so we just generate a synthetic noise and then add synthetic noise to clean speech. So that's generally people are doing. But unfortunately, such synthetic noise does not generate so well in reality. Then our case, so we can apply this PU classification. And positive is actually noise in our case. Then we put a microphone in some noisy environment and collect noise. These are already positively labeled data for us. Then we ask somebody to speak in the noisy environment. Then this is a mixture of speech and noise. So this is actually unlabeled data for us. Then that's it. So we have two sets of P and U data and just train a classifier. Then we can separate the speech and noise. And then so compared with the supervised baseline, so still our method is a bit inferior, but compared with the previous approaches, our method is much better than the previous approaches. It's a simple application of PU classification, but this seems to be quite useful. Then that was about PU classification. But then, so we can basically use the same recipe for many different weakly supervised learning problems. we have a lot of examples, but let me just explain one more thing. So it's called UU classification. Yes.
Sorry, going back to the previous slide. What is the instance that's being classified here? Is it like a
right.
time frequency?
Yeah. So we apply short-term Fourier transform and time frequency domain, and we took a patch. So this patch is a sample. So because of this Fourier transformation, so it's a mixture of situations. Thank you very much for the clarification. Yes, then more extensions, and let's talk about UU classification. It's called unlabeled classification. It's actually the most challenging scenario in weakly supervised learning problem. We don't have any single labels, but instead we have two sets of unlabeled data, and we know that class proportions are different. The class conditions are the same. Then actually we can still train a classifier with guarantee, and we can perform empirical risk minimization. And the naive intuition is like this. So suppose there are two hospitals and they have many medical images, but medical doctors are so busy, all of them are unannotated. But we have prior knowledge that in hospital A, 20% of the patients are cancer. And then hospital B, 30% of the patients are cancer. Then this is enough. So two sets of unlabeled data and class proportions. Okay, we can train a classifier. And given the medical image, we can predict whether cancer exists or not.
Do you assume that the class conditional?
The conditional are the same.
Yeah.
So then like we have two Gaussians and only mixed.
So the two hospitals use exactly the same X-ray machine.
Yeah, okay, that's a hypothetical scenario.
Yes,
so,
that's fine.
Yeah. But without having any single label, we can learn the boundary. But of course, we don't know which side is positive or negative. So we need maybe one sample to know the direction. Otherwise, we can have a boundary only from unlabeled data. And basically, the convergence rate is the same as the supervised learning case. Then also we have a lot of multi-class extensions, but today I don't really go into the detail. But essentially, we can apply the same kind of recipe, unbiased risk estimation and non-negative correction. Then we had a book on this like empirical risk minimization approach to machine learning from weak supervision, so 3 years ago. Then, so after that, we also made a lot of progresses. Like we tried to have a mathematically unified frameworks for many different problems. And also we explore new problems and new algorithms. And more applied side, so we apply weak supervision to imitation learning and also large pre-trained models. So this is nowadays becoming quite important. We're also submitting new papers even this month. Okay, that was about weakly supervised learning. And do you have any questions so far? Okay, good. Then let's continue. The second part is quite short. It's noisy labeled learning. So here we consider very standard supervised learning problem with noisy output. So in the case of one-dimensional regression, so it's like this. We have input X and output Y, and we have X and Y bar. So Y bar is a noisy output. We have this. Then usually we don't care, so we just fit our model to noisy output. In the case of classification, so we have label flipping noise like this. And again, X and Y bar, and we don't care, we just fit. So this is what we are doing in practice. But is this done already? So for regression, maybe yes. As long as noise is mean zero and additive, so just having large number of noisy output is fine. If we fit the function, we can noise is automatically cancelled, and we have a consistent solution. But for classification, so still actually we need more research. So it's surprising, it's such a simple problem, but it's not solved yet. So we need a specific noise reduction mechanism to achieve consistency. To approach this problem, one potential standard approach is called correction with noise transition. So here we consider so-called noise transition matrix T. So it's a probability of flipping a label from I to J. So in the 3-class problem, so we have 3 by 3 matrix like this. Then 1, 0, 0 means class 1 label is always class 1. It doesn't flip. At 0.1, 0.8, 0.1. So this means class 2 label is only correct with 80%. And it becomes 1 or 3 is 10%. Then 0.5, 0.50. So this is a bit strange case. That class 3 label is never class 3, but it always becomes class 1 or class 2 with 50%. So by the way, this is what we call complementary label. It's exactly one form of weak supervision. And we can train the classifier only from wrongly labeled data. So this is actually this situation. By the way, anyway, so noise transition matrix T contains a lot of precious information. And if it is given, then actually we can solve the problem quite nicely. So this was proposed by Patrini et al. In 2017. So one is called classifier adjustment. So T is essentially a noise process. Once classifier output is applied to T transpose, then we can somehow simulate noise. Then this noisy classifier is fitted to noisy labels. Then we can recover consistency. So that's one approach. Then another approach is called loss correction by T inverse. So T is a noise process, then T inverse is a kind of denoising process. If you consider a vectorized version of loss functions and apply it to T inverse, then okay, we can somehow eliminate the influence of noise, and we can have an unbiased mixed estimator. So these are sometimes called forward correction and backward correction. These are quite systematic nice approaches. But we need the knowledge of T, and this T is not available in practice. And we need to estimate it from only noisy data. So that's a big challenge. And actually, this estimation of T is quite related to estimation of the class prior pi in the case of weakly supervised learning. And in both cases, I must admit that it's not actually solvable mathematically without having additional conditions. The posterior class prior pi is not estimable, and also noise transition T is not estimable. But if we have some additional conditions, we can estimate it. So that's why we spend several years to somehow estimate T based on some human cognition properties or some mathematical tricks. And in the end, we had a relatively reasonable solution in 21. So let me briefly go through this technique. It's called volume minimization. So for illustration purposes, let's consider a three-class problem. So we have a triangle that corresponds to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then the noise transition matrix is actually a simplex like this, a triangle included in this big triangle. Like first column, second column, and third column like this. It's a true one. Then interestingly, the noisy training data is, so by definition, they are mapped in this simplex. So X and Y bar are plotted in this way. We don't know those points and we don't know the triangle, but we can have this relation mathematically. Then, so our algorithm is like this. So we prepare some initial solution, initial triangle. Then, so we try to contain all training points inside, and at the same time, we try to minimize the volume. Of course, if we consider the biggest triangle, we can contain all points, but now we shrink the volume and try to have the minimum volume simplex that contains all training data. And this can be achieved by minimizing the training loss. So this corresponds to including all points inside. Then this regularization term, some volume measure is coming here, and we minimize both of them. Then actually we can justify this approach in two ways. First, so suppose our training set endpoints contains several noiseless labels. We don't know which one is noiseless, but assume they exist. Then actually those noiseless points actually correspond to the vertices of the triangle by definition. Then, so it's obvious that by shrinking the volume, we can recover the true triangle. That's one justification. Then another one is, so even without noiseless labels, so we don't have points on vertices, but as long as our training data is what we call sufficiently scattered, so labels are quite diverse enough, then actually we can still identify the true T. So we have mathematical conditions in the paper, but I don't really go into the detail today. But intuition is like this. So here we have 2 points on each edge like this. Then, so in this case, by shrinking the volume, we can still recover the true triangle without knowing the vertices of the triangle. So that's a kind of intuition. So of course, maybe this condition may not be exactly satisfied, but as long as our noisy labels are diverse enough, then we can approximately obtain the true triangle, true T. So this can be used in practice for noise robot. So to the best of our knowledge, this is one of the best approaches to estimate T only from noisy labels. So the problem was almost solved. But unfortunately, the real-world noise is even more challenging. And what we have considered so far is so-called input-independent noise, or class-conditional noise. So this means that noise property is the same over the entire domain. But in practice, so maybe we have more noise near the decision boundary, because those points are more difficult to label. Then, so to handle such an input-dependent noise, we need to consider input-dependent noise transition matrix, or noise transition matrix function like this. So even if T is a constant matrix, its estimation was extremely challenging. But now it's a function of X, so it's almost impossible to estimate it. So we end up in finding some heuristic solutions, and we have reasonable methods so far. But in the end, so we found that maybe this is not really the promising approach to really solve the problem. So I will come back to this point later. But nowadays, we try to have a completely different approach to tackle this input-dependent noise. Okay, that was about noisy label learning. And do you have any questions so far? Okay, great. So let's come to the transfer learning part. So now the training and test data follow different distributions, maybe due to changing environments over time or due to sample selection bias, due to some privacy concerns. So the goal of transfer learning is to train a test domain predictor using training data from different domains. That's a standard problem. And apparently this is not a new problem. And okay, I co-organized a workshop at NIPS in 2006. And at that moment, there was no name for this problem. And our workshop was entitled, so NIPS workshop on learning when test and training inputs have different distributions. So this really explained the meaning of the problem. Then, so the workshop was actually quite successful and we had a lot of great speakers. And after 3 years, so we published an edited volume from this workshop. And at this moment, so we named it Dataset Shifting Machine Learning. But unfortunately, this name, dataset shift, did not become popular and it was completely forgotten. So, but recently, so this problem is back. But we have more fancy name now, the distribution shift or fine tuning. And at New Rips in the last 4 years, there are workshops on distribution shift and fine tuning like this. I am also involved in part of them. So dataset shift is completely forgotten, but this book is now actually cited a lot. Maybe this book is not sold quite well, but citation is increasing now. It's quite interesting. Then here's the basic. So we stick to an approach called importance-weighted training. And to explain the concept, let's focus on the simplest situation called covariate shift. So covariate is the name of input variables in statistics. And covariate shift means only input distribution changes. So X is input and Y is output. The P of X changes between training and testing. And P of Y given X doesn't change. So that's the covariate shift assumption. And it can be nicely illustrated in one-dimensional regression, like horizontal axis input and vertical axis output. And we have the fixed target function, red one. Then input distribution only changes. So in the training phase, we have blue point training data from the left-hand side. Then in the test phase, we have test points from the right-hand side. Then if we just perform naive linear least squares, we just end up in fitting blue points and obtaining this green line. So ordinary training is not consistent. It doesn't predict black points quite well, black crosses quite well. But once we apply importance weight to the loss function, so importance is the ratio of PT of X over PT of X, then so from blue points and importance values, we can obtain this green line. It predicts black crosses quite well. And we can show that it is consistent. And in this illustrative example, actually most of the points have almost zero importance. And only a few points on the right-hand side have large importance values. So by this importance weighting, essentially we are selecting samples that are important for test distribution. So this can be automatically done based on this importance weighting. Then the question is, how do we estimate the importance? This has been a long studied topic, and I also spent a lot of time, more than 15 years ago. Then, so classic approach was like 2 steps. So first, we estimate the importance from unlabeled training data and unlabeled test data. Like one of the approaches is called least squares importance fitting, and this is quite simple. We have the true importance value here, and our importance modeling is here, R. And we consider the square difference between these two and take the expectation. Then actually, if we apply an empirical approximation, then everything can be actually computed only from training input data, test input data. Then we can have a consistent solution, R hat. Then use this R hat as an importance weight in the second step and obtain the final predictor F hat. So we explored this kind of two-step approach a long time ago, and we had a lot of nice industrial applications at that moment. But still, there's a clear drawback of this approach. It's two steps. So because of the two-step nature, small estimation error incurred in the first step can be magnified in the second step. It's not necessarily an optimal approach. Then after 10 years, so we finally had a new approach. It's joint weight predictor training. So we try to have R and F, estimate R and F at the same time. So I don't really go into the detail, but we just have a upper bound on the test risk. And more precisely, test risk squared divided by 2 is upper bounded by J function. And this J function is interestingly exactly the sum of these two terms. Then we minimize this with respect to R and F. So this means that the previous two-step approach is clearly supportable. It minimizes the upper bound in 2 steps. And now we can minimize them jointly, and we can justify the solution. So that works actually much better. Okay, that was about covariate shift. Then more recently, so we are interested in so-called sequential shifts. So far, we only consider the training and testing distributions, and now test distributions can change over time. And we want to somehow perform online learning over this changing distributions. And our setting is still quite the same. We have labeled training data and unlabeled test data in each time step. And we want to update. Basically, we do online gradient descent over time. Then, so we had 2 approaches so far. So sequential label shift, where only P of Y changes over time. Or sequential covariate shift, so only P of X changes over time. And basically, this is a kind of application of online convex optimization. So we only learn the final layer of the neural network, and we fix the feature extraction part. Then we can apply online convex optimization theory. And we can show that, so even without knowing the amount of distribution shift, we can somehow minimize this dynamic regret over time, like this. And this is a very strong result. But this can be achieved only from unlabeled data in the test phase. Then finally, so I want to combine these 3 independent topics together because it is more challenging and important. Okay, we spend a lot of time to discuss distribution shift problems, but many distribution shift works focused on a particular shift type, like covariate shift in our case. But in reality, so identification of the shift type is the most difficult part. In particular, our case is so-called unsupervised domain adaptation. So only labeled data from the training domain, and only unlabeled data is coming from the test domain. Then, so there's no way to know about output values in the test domain. Then it is actually impossible to know whether the current shift is covariate shift or whatever shift. So it's more like a belief. So we assume it is covariate shift and apply a method. If it works, it's great. If it doesn't work, let's consider another approach. So that was the kind of practice so far. Then another issue is the label noise. So actually, label noise is a type of distribution shift. So P of Y given X actually changes between training and testing. In the training phase, we have noisy labels, Y bar. And in the test phase, we suppose we have clean labels, Y. And we want to predict them. So then this is actually exactly the distribution shift problem in P of Y given X. And we have noise transition here. And as I said, if the noise transition is input independent, so X can be eliminated, then so we have a reasonable method already. But if it's input dependent like this, then still this is a quite challenging problem. Then our approach here is to consider a more generalized situation called joint distributions. Now P of X and Y, joint distribution changes between training and testing. basically this contains everything. So once we have a reasonable solution to this setting, then so almost all headaches are gone. We can just apply that method to solve a challenging problem. And so far we had one method to tackle this problem. So it's called mini-batch-wise loss matching. But the biggest assumption in this paper is that so we need a small number of labeled test data. So we have now X and Y data from the test domain. If we have a large number of labeled test data, then we just train the system with that. We just assume it's small. Then, so we prepare a neural network and apply standard stochastic optimization. Then here we want to perform importance weighting dynamically in the mini-batch wise manner. So we estimate the importance weight only from a mini-batch of training and test data. Then, so I don't really go into the detail, but we use the method called kernel mean matching for estimating the importance weight. And in particular, so we apply kernel mean matching for loss values. So we don't really consider the distribution, entire distribution, but only the distribution of the loss values. It's a one-dimensional quantity. So this is how we handle this importance estimation problem in the mini-batch. And we must admit that this is nothing accurate. The problem is extremely simplified. But actually, this is fine because so this is just one of the 1,000 steps of stochastic gradient descent. So as long as we can find some reasonable direction to go, then it's fine. We just continue this many times, and then we can obtain some practical solution. Of course, there's no serious justification for this approach, but this method seems to be somewhat useful in practice. The more extensions are ongoing nowadays. So one of the clear limitations of this importance weighting techniques is that the training domain must contain the test domain. Like PTE should be wider than PT. PPTR should be wider than PTE. Otherwise, the importance value tends to increase. So previously, I showed a linear regression example, and it looks like an extrapolation problem, but it was actually not really true. We had training data from the left-hand side. It was actually drawn from a Gaussian distribution, and it had pattern tail, long tail. Then test distribution was actually included in this tail. This is how we computed the importance in that application. But in reality, we want to really solve a problem like this. The test distribution sticks out from the training domain. This is a real extrapolation setting. So how can we handle it? So we applied an outlier detection technique to identify this point. Once we know this point, we can split our test data into the training part and test part. So we are still following the same setting as this paper. So we assume we have a small number of labeled test data. Then now we have labeled test data in the training side and test side. Then for the data in the training side, we apply a standard importance weighting technique for joint importance weight. And for the test data in the test side, we just use their loss directly, their precious test data. Just add them up. Then we can justify this approach. So we can really do extrapolation in this case. But still, this is really demanding. We need a small number of label data from the test domain. For example, if we consider like label noise problem, then having label test data basically means we have clean labels, noiseless labels. So this is too strong. So we want to somehow mitigate this situation. But if you only have unlabeled data from the test domain, then there's no chance to identify joint distribution shift and copy it. So our practical solution we are thinking of is to combine weakly supervised learning ideas here. At least for the classification problem, we have shown that only from weakly supervised data, we can really solve a classification problem in the same way as supervised learning. And we are wondering whether same kind of idea can be applied to the joint distribution shift. So we don't require fully labeled data from the test domain, but instead some form of weak supervision is available from the test domain. But hopefully this weak supervision is sufficient to solve joint distribution shift problem. So this is still just a direction, and we don't really have an answer to the question. But I think this is one of the promising directions. Then once we have done this, we hope to extend it to sequential distribution shift. It's more like a continual learning. So maybe we should also extend it to like a limited memory setting or no memory setting. And it's a real continual learning system. And hopefully we can give a nice theoretical approach to this question. Then in the end, we hope to have a machine learning method that works with least assumptions. Because nowadays, many people spend a lot of time to really have a kind of champion performance, like assuming a lot of prior knowledge and assumptions. So this is, of course, quite important and one way to go. But in many like new applications, so we don't have data yet, we don't have people yet, we don't have knowledge of the problem yet, then we can't really apply state-of-the-art machine learning techniques in those new problems. Then, so what we want is a kind of quite simple method that does not really require strong assumptions. And maybe the performance of that method is not so good, but as long as it has minimum guarantee, then we should be able to somehow test whether machine learning is really useful in that application or not, without investing a lot. Right. So then, okay, once we understand that we found that machine learning is somewhat useful, then we should ask our boss to invest more money and assign more people. Then we have more knowledge on the problem. Then we should be able to use more sophisticated machine learning method as the second step. So we are completely missing the first step of this kind of machine learning with weak assumption, least assumption. So this is something we are trying to explore nowadays. We don't really have a definite answer to this question yet. And also, there's no single answer. There must be many different approaches in this field. But hopefully, this kind of machine learning with these assumptions is quite useful in many applications. And also, it stimulates theoretical research in this field. Okay, thank you very much. That's all for.
Thank you. Yeah.
So in practice, there's a lot of fine tuning going on.
Mm-hmm.
Train a big model and fine tune. What's your intuition about the in-practice relationship between sort of an unjustifiable fine tuning?
Yeah. So
more theoretical.
Yeah. Last year at NeurIPS, we had a fine tuning workshop and we had a panel discussion. And then there actually I posed a question. So maybe the word fine tuning is not a good idea. It's more like an engineering tuning of the model, but it should be online learning. So given the data from downstream tasks, it's an online learning, adaptive learning problem. So we should really take that problem seriously into account. Because otherwise, many people just collect new data and just fit it. So it's really engineering approaches. So hopefully, this could be one of the approaches. So joint distribution shift adaptation is one of the, I think, promising ways to discuss, address fine-tuning.
So from the online perspective or joint perspective, how does this relate to mammal?
Because in practice, we don't really know whether the shift is covariate shift or whatever shift. So this is part of the weak assumption approach.
But there's this well-known approach to meta-learning.
Yeah.
Mammal.
Mm-hmm.
Is that related?
Yeah. So meta-learning is one of the another families of that line of research. I think there are many different approaches, but hopefully they are really systematically discussed in the context of fine-tuning. But nowadays, fine-tuning communities are more empirical.
So here, your observed label set is always the same as your true label set, just shifted or different.
Yeah, so in those papers, so we have assumptions on label shift or covariance shift. So we only observe unlabeled data in the test phase.
But I guess I'm wondering how this relates to situations where what I think of more transfer learning, where you really have different tasks observed during, you have observations for different tasks that are just related to the tasks of interest.
But in the context of LLMs, for example, then news is happening every day.
Right.
So then people's emotion may change, or required answer is also changing. So we want to naturally tackle, follow this kind of change. So that's a natural story, I think.
Okay. Any other questions? Okay, let's thank Masashi again.
Yeah, thank you very much.